we solved an equation like x plus 3 quantity squared equals 5. That might be the exact one we did actually. But so we solved equations like this by taking the square root of both sides, which we can do because the left side is a perfect square. There's nothing going on outside the parentheses other than that exponent. And then the right side is a constant. That's how we know that we can use that square root property to solve. So we get x plus 3 equals plus or minus the square root of 5. And then we subtract 3 from both sides. So negative 3 plus or minus the square root of 5. And those are our solutions. So that's pretty nice. It's pretty quick. A lot quicker than like multiplying out that x plus 3 times x plus 3. The problem with it is that you will rarely get equations in this form. Like, it's pretty convenient that we had that perfect square and then we had a constant on the other side. It's not usually like that, right? Usually it's like something times x squared plus something times x plus a constant. And so we need a process for writing equations like this if we want to use that square root property. And what we're going to do is called completing the square. So we're going to do an example first and then we'll generalize. So if I want to solve, say, x squared plus 8x minus 10 equals 0. Well, the first thing I would do is try to factor, because that's the simplest way to solve an equation, a polynomial equation, and it leaves the least amount of room for error because there's not a ton of calculations. So if I could factor, I would solve by factoring, but unfortunately x squared plus 8x minus 10 does not factor, and so we have to throw our factoring strategy out the window. But I know that if I have a constant on one side and a perfect square on the other side, that I can take the square root of both sides, right? So let's look at what a perfect square looks like. So x plus 3 times x plus 3 well, I always have two of the same terms in the middle, right, that combine to give me that coefficient of the middle term. And then this number is always a perfect square because it's always the constant of the binomial that we're squaring, just squared, right? When you multiply constant terms, you get the constant term. So that constant term is always a perfect square. And when I look at this, I notice that 10 is definitely not negative 10 is definitely not a perfect square, right? And so this is not going to it doesn't factor at all, but definitely isn't going to factor into a perfect square. So what we're going to do is we're just going to change that constant. So we're going to start by adding 10 to both sides, so equals 10. So I just kind of got that constant out of the way so that I can replace it with one that will actually give me a perfect square. And then we're going to look at this geometrically because a square is a geometric thing. I'm going to express the left side of this equation as some shape, which I eventually want to be a square. So we will start with x squared. So the area x squared can be obtained by a square with x on either side, right? So x times x gives me x squared. And then if I want to represent that 8x, it's like 8 times x, right? So if I had a length and width of 8 and x, that would give me an area of 8x. So I could like put something over here and then make that width 8. And then you guys see the area is 8x. Well, that's all well and good, except it looks nothing like a square, right? It just is a big rectangle. And our goal is to have a square so that the length and width are exactly the same. So this isn't going to work. I want something symmetric. So instead of doing that, I'm going to make 2 rectangles. I'm going to put one here, and I'm going to put one here. And in order for this to be symmetric, those better be the same size, right? So if they have to add up to 8x, what should the area of each of them be? 4x, right? So 4x, 4x. So on that top right one, we see the length is x, so this width must be 4. And same thing here. That's a 4 by x rectangle. So this is hopeful because the distance across the top is just x plus 4. And the distance down the side is also x plus 4, the total distance. And so this is a lot like a square because the length and width are the same, but it's missing something. What's it missing? Yeah, it's missing that corner, right? So if I put this corner in, then I'd have a square. What's the area of that square that I just put in the corner?
X minus 4.
So look at the length and the width. Yeah, it's 16, right? It's a 4 by 4 square. So if this area, the total area, were written as a polynomial, it would be x squared plus 8x plus 16, right? So I have the x squared and I have the 8x. Am I allowed to just add 16?
No.
Why not?
Because that wasn't in the equation.
This is true.
Would you add it to both sides?
Yeah, so I'm not allowed to just add it where I want it, but I can add it to that left side if I balance it out by adding it to the right side, right? We can basically do anything we want to an equation because there's those two sides that stay balanced. So I'm not allowed to just change one side, but I am allowed to change both sides in an equivalent way. So I can add 16 to both sides. And that gives me x squared plus 8x plus 16 equals 26. So another way to represent the area of that big square is to multiply the length times the width, right? So x plus 4 times x plus 4 better be the same as x squared plus 8x plus 16. And if you do your AC method, you'll see that it does in fact factor into x plus 4 times x plus 4. And now we've got an equation in the form that we want it, so we can take the square root of both sides. Here's 26, so we have x plus 4 equals plus or minus the square root of 26. And x equals negative 4 plus or minus the square root of 26. So this might seem like a lot at this point, but solving by completing the square is actually really, really simple once you get the hang of it. So once you do a couple, you'll find that like really all you have to do is figure out what to add to both sides. And once you get the hang of that, yes?
Should we leave the plus or minus square root alone, or like this one we could factor out 16 from it to have 4 times whatever's left?
So you do always want to simplify them, but this one you can't factor out a 16 because that, are you thinking 10 plus 16?
No, I'm thinking that 16 is 4 times 4.
16 is 4 times 4, but 26 isn't 16 times anything. Like we can't factor 26 as 16 times something else. Like if we factored 26, it would be 2 times 13. And neither of those is a perfect square. So you're absolutely right. We would want to simplify this if we could. But unfortunately on this one, we can't simplify it because there's no perfect square factors under my radical. But I'm glad you brought that up because you definitely would want to simplify it if you could. So,
Have the plus
go
or
ahead.
minus in front of it.
Yes. So the other thing about completing the square is that there are other ways to solve quadratic equations, which we'll talk about here in a minute, which means that you don't have to complete the square to solve. However, completing the square is a tool you'll use in a lot of applications in your other math classes. And that's one of the reasons we even bother to teach it, is not so much because you have to use it to solve an equation, but because the process of completing the square is something that you'll use later on, especially if you take 151, because you have to use it to write equations of circles, and trigonometry is all about circles. So it's a process that you want to know how to do, even if you don't plan on using it to solve quadratic equations, because there's other ways to do it. So definitely practice it. I'm not going to say that you have to solve by completing the square, but the more practice you get with it now, the easier it's going to be later on when you use it again. And like I said, once you get the hang of it, it's actually way quicker than the other method. Like it goes really, really fast. So let's generalize the process we use so we don't have to draw a square every single time. So what we did was we started with an equation of the form x squared plus bx plus c. Notice that the coefficient of x squared is 1. You can only complete the square if the coefficient of x squared is 1, because the whole thing rests on this square right here that has an area of x squared. If that first term was like 2x squared, we can't make a square to represent that, right? It would have to be like 2x by x, which isn't a square. So first things first, if the coefficient of x squared is not 1, divide both sides by it. So the coefficient has to be 1, but that's okay because it's an equation. And so if I have like 2x squared, I can just divide both sides by 2. And then the coefficient will be 1. The next thing you're going to do, well, what did we do when we did our example to start with? Yeah, we got the constant on the other side, right? So we got all variable terms on one side and the constant on the other. So in this case, that would give us x squared plus bx equals negative c. And then we started looking at this shape, which wasn't quite a square to begin with. But how did I get that 4? Like first I started by drawing one rectangle that had an area of 8x, and then I said, oh, that's not symmetric enough. So how did I decide on 4?
Because half of 8 is 4.
Yeah, exactly, because I want to split it between 2, and so I took half of that coefficient. So the coefficient of x divided by 2. And we can see if you add b over 2 plus b over 2, you get b, right? You get 2b over 2, which is b. So what would that make the area of this little square that we have to add? So look at the length and the width of that square. What would the area be? I've got all day.
Would it be b over 4?
So how'd you get that?
Just multiplying the denominators.
So why do you only want to multiply the denominators?
That would be the square, I guess. I don't really know.
So if the length is b over 2 and the width is b over 2, then the area should be what?
b over 2 squared.
Yeah, b over 2 times b over 2. Nice synchronicity there, guys. That was awesome.
Yeah, we're pretty good. Didn't want to say anything about it though.
Squared. And so that's the number that we have to add to both sides to complete the square. It looks more complex than it is, like, because it's a fraction, I guess. But all that is saying divide that coefficient by 2 and then square the result of that. So we're adding b over 2 squared to both sides. And then we have to factor the left side, right? Because that's the whole point of this, is that we can factor the left side as a perfect square. And I ran out of room for my last step. We're going to factor the left side. And it turns out it always factors the same, because the entire area of that square is just its length times its width. So it factors as x plus b over 2 quantity squared. And you don't have to really remember that, because you can just factor using the AC method and you'll find what it factors as. Where that is kind of convenient is if you have fractions, because we haven't really factored with fractions. So if you kind of know what it should be, that can be helpful in factoring when you have fractions. And then the last step is just to solve using, I mean, this is all of completing the square, and then we can take the square root of both sides to solve. So b over 2 squared equals negative c plus b over 2 squared. So to complete the square, you just want to follow those steps. And again, it looks like a lot more than it is. Once you do it a few times and get the hang of it, it works out pretty nicely. So let's do another example. We'll solve 2x squared minus 12x plus 9 equals 0. So what should I do first?
Get rid of that 2.
Yeah, so we're going to divide both sides of the equation by 2 because I want the coefficient of my first term to be 1. So we have x squared minus 6x plus 9 halves equals 0. What next?
Subtract
Uh-huh.
You like prefer fractions, like in
Definitely.
fractions over mixed numbers, right?
Oh, definitely over mixed numbers, yeah. In order to do anything with mixed numbers, you have to make them fractions.
It's so hard, but it just looks so much better.
So now we're at the point where we're actually going to complete the square. So what should I do? Dylan, what should I do next?
Draw your square.
We don't have to draw a square,
Add b squared to both sides.
not b squared.
B over
B
x.
squared.
Dylan, what do I do next?
I would add 6 or split 6x, so it's 3x, and you would have 2x.
So b is negative 6. We divide it by 2 and square it. So negative 3 squared is 9. Now, we don't change that 6. Like, we're not dividing negative 6x by 2. What we already have stays exactly the same. All we're doing is using that negative 6 to figure out what number we add to both sides. We don't actually change that negative 6x. So we found 9. We'll add that to both sides. So x squared minus 6x plus 9 equals negative 9 halves plus 9. And now we can factor the left side. It factors into x plus 3. Whoops, no it doesn't. It factors into x minus 3 squared. And negative 9 halves plus 9 is positive 9 halves. And if you didn't know that that factored into x minus 3 squared, that's okay. Just use your AC method to factor it. You'll get the same thing. And now we can take the square root of both sides. So we have the square root of x minus 3 squared equals plus or minus the square root of 9 halves. So x minus 3 equals plus or minus. Well, the square root of 9 is 3. And the square root of 2 is just the square root of 2. And in situations like this, we typically rationalize the denominator because I'm going to add 3 to both sides, and I'd rather get common denominators and have the answer be a single fraction than have 2 separate fractions or 2 separate values. So I'm going to multiply by the square root of 2 over the square root of 2. And now we can add 3 to both sides. So x equals 3 plus or minus 3 root 2 over 2. And then 3, oh, what's up? Oh, you're furrowing. 3 over 1 is the same as 6 over 2. So this is 6 plus or minus 3 times the square root of 2 over 2.
Why?
3 over 1 is the same as 6 over 2,
Okay.
right?
Yeah.
So I just got common denominators. And don't go crazy starting to cancel here because we can't cancel anything. The numerator is not a product, right? It's got addition, subtraction in it. So theoretically, I could factor out a 3 here, but that wouldn't help me simplify the fraction at all, because the only thing we have on the bottom is a 2. So we can't simplify this at all. Yes?
So like if we just leave it like the 3 plus or minus 3 root 2 over 2, that's
Uh-huh.
wrong.
Sure. What you're really asking is, can you not do what I'm telling you to do and still get a good grade? And so I'm gonna say that it's wrong, even though it's not wrong, because I want you to do it this way.
Okay.
Other questions? Okay, so we're going to solve one more of these. We are going to solve ax squared plus bx plus c equals 0. What should I do first?
Remove the A.
We're going to divide both sides by a. So we get x squared plus b over a x plus c over a equals 0. Because 0 divided by a is 0. What next?
Remove this.
So x squared plus b over a x equals negative c over a. And now I have to figure out what to add to both sides to complete the square. So remember our process. We take the coefficient of x, which in this case is b over a. We divide it by 2, and then we square that. Well, when you divide a fraction by a whole number, so if you divide a fraction by 2, that's the same as multiplying it by 1/2. So really that whole number in the denominator just becomes part of the denominator of the fraction in the numerator. So it's b over 2a. Because that's what you would get if you multiplied b over a times 1/2. And then squared, which is b squared over 4a squared. So that's what I'm going to add to both sides. So b over a times x plus b squared over 4a squared equals b squared over 4a squared minus c. And now we have to factor, yeah?
Why isn't it minus c over a?
Oh, it is.
Oh.
Thank you. So now we're going to factor the left side, which, again, we haven't really factored with fractions, certainly not with fractions that have all these variables in them. So let's go back to what we know it factors as. So it's always going to factor as x plus whatever it was we squared to get the number we added to both sides, right? To the second power. So it's always that coefficient of x divided by 2, because that's what we wanted to be like the width of those rectangles. So in this case, this is the coefficient of x divided by 2. So we factor into x plus b over 2a squared. And then over on the right side, I'm going to get common denominators so I can add those. So I'm going to multiply by 4a over 4a so that both fractions have a denominator of 4a squared. So b squared minus 4ac over 4a squared. Now we can take the square root of both sides. So we have the square root of x plus b over 2a squared equals plus or minus the square root of b squared minus 4ac over 4a squared. So on the left side, I just get x plus b over 2a. And on the right side, if I take the square root of the top, that doesn't simplify, so b squared minus 4ac. But the square root of the bottom is 2a. So make sure that that radical is only in the numerator. We don't have a radical in the denominator because we were able to take the square root of the denominator. And then there's only like one more step to this, which is to subtract b over 2a from both sides. And conveniently, those have common denominators, so we can add the numerators. We'll add and subtract the numerators. And we get negative b plus or minus the square root of b squared minus 4ac all over the common denominator of 2a. This is what we call the quadratic formula. You need to memorize it. So the quadratic formula is the third way we have of solving quadratic equations. The downside of the quadratic formula is that it's really only useful for one thing. Like the only thing it does is solve quadratic equations. Whereas completing the square has a lot of other applications in math. So it's like a more useful skill to have than just plugging numbers into the quadratic formula. The only place I really use the quadratic formula is like in application problems. So if you have like decimals in your equation, then the quadratic formula is useful because it's kind of a pain to work with decimals as far as factoring goes.
You can make them into fractions, like that's what you're talking about, right?
Making the decimals into fractions?
Yeah.
I mean, you could.
Okay.
Usually we come across those like in application problems though, and like so it has to do with money or something like that. So
You can't make them.
we could make it into a fraction, but we'd have to make it back into a decimal. So it just makes more sense to do some calculations with the decimals rather than trying to do fractions and factor and all that stuff. So we're going to solve 3 equations using the quadratic formula. These are equations I wouldn't normally solve using the quadratic formula. I just have a point to make, so we'll do it this time. And it's a little practice. So let's solve where are they? Here they are. X squared plus 2x minus 9 equals 0. Actually, I'm going to make this not a 9. No, I'm going to make that not a 2. I'll make it a 3. There we go. So A is 1, B is 3, and c is -9. And then we can just plug it in. One thing that'll help with memorizing is if you actually write the quadratic formula like every time you use it before plugging numbers in. So just with the A's, B's, and C's. That way every single time you do a problem, you're like helping yourself internalize it. We'll just write it up here. X equals b times the square root of b squared. Make sure that you've written that down correctly. That way you're not memorizing something that is not correct. That negative b is part of the numerator, right? It's not in front of the fraction, so make sure that line is long enough that your negative b is in the numerator. And then the radical is not over the 2a, right? It's only over that b squared minus 4ac. Kenny, could you swing that door shut for me? So just make sure it's written exactly like that so that you memorize it correctly. So we have x equals -3 plus or minus the square root of 3 squared minus 4 times 1 times -9 over 2 times 1. Do yourself a favor and put 3 squared minus 4 times 1 times -9 all in your calculator all at once. The most common error with these is a sign error in that whole -4 times 1 times -9 region. So if you put that whole thing in your calculator, then your calculator will take care of the signs for you and you won't risk messing them up. So all at once, what do you get? 36, 45? Dang it. I wanted one that didn't simplify. Oh well. And normally I would simplify the square root of 45, but that's not the point right now, so I'm just not going to.
My calculator keeps giving me -27.
Are you
have +4 instead of -4?
Are you typing it in all at once?
Yeah.
And you typed 3 squared minus 4 parentheses 1 parentheses -9? Did you? Oh, yep. That'll do it. Okay, next one. Let's solve.
Okay,
Okay.
it's like, never mind.
You sure?
I'll figure it out later.
Okay. Oh, question. How many solutions did we just get to that equation?
2.
We got 2, right? We get one solution using the plus and one solution using the minus.
But we can write it like that,
Uh-huh.
with the plus sign.
So this is 2 real solutions. And we only care about real solutions because one of the main purposes of this is to find the x-intercepts of a graph. And graphs only have real numbers on them. Like there's no imaginary numbers on your graphs. So if we find 2 real solutions, that means that the graph of this function has 2 x-intercepts. Whereas if the solutions weren't real, we wouldn't really care because it would have no x-intercepts. So let's do 5x squared plus 2x plus 8 equals 0. So A is 5, B is 2, and C is 8. We get x equals -2 plus or minus the square root of 2 squared minus 4 times 5 times 8. Go ahead and plug that in your calculator. All over 2 times 5. And we get x equals -2 plus or minus the square root of what? What'd you guys get?
-1/6.
Good. All over 10. How many real solutions does this equation have?
2.
None because it's a negative and a square root.
Right, so we can't take the square root of a we can take the square root of a negative and get an imaginary number, but as far as real solutions, the square root of negative 156 is not a real number, right? Remember how when we find domain, we say the radicand has to be positive, right? So if it's negative, we don't get a solution. So we have 0 real solutions. Do you guys all have your quadratic formula written down? Okay, I'm going to erase mine. Then the last one we'll do is,
So why couldn't you take the negative and multiply it into the 156 to get a positive and that be one real solution?
because negative 1 times the square root of negative 156 isn't the same as the square root of negative 1 times negative 156. Like if you have a 2 right there,
Yeah.
that's not the same as 2 times, or the square root of 2 times 10, right?
Okay, yeah.
Just gonna make this one simpler. Plus 6x plus 9 equals 0. Yes.
I just have a quick question.
Uh-huh.
Why aren't we doing it just like removing the 4? Like why are we doing the quadratic formula instead of the other way? Because this one's easier, or?
No, because I have a point to make.
Oh, okay.
So A equals, I only use the quadratic formula like when I can't factor, and completing the square is more work than the quadratic formula.
Okay.
6 and C is 9. So X equals negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 9 all over 2 times 1. So X equals negative 6 plus or minus the square root of 0 over 2. How many solutions do I have now? So normally we get 2, right? We get 1 solution from adding and we get 1 solution by subtracting. But negative 6 plus 0 is negative 6, right? And negative 6 minus 0 is also negative 6. So really you just get 1 solution because addition and subtraction give you the same thing. So 1 real solution. And what we looked at when we figured out how many solutions there were really is what I have in red. Oops, that one's not red. So what the radicand of that square root is really what told us how many solutions, right? Because when it was positive, we were like, oh, we get 1 solution by adding that number, 1 solution by subtracting it, so that's how we get 2. When it was negative, we said we can't take the square root of a negative, so we have 0. And then when it was 0, that caused us to get the same thing when we add and subtract. And so that's what gave us 1 real solution. So you can figure out how many solutions you have without actually finding them using what we call the discriminant. And the discriminant is just b squared minus 4ac. It does not include the radical. It's just what's under it. And if d is positive, we found that we have 2 real solutions. If d is negative, we found that we have 0 real solutions. And if d is equal to 0, we have one real solution. And remember, the solutions to these equations correspond to the x-intercepts of the function's graph. So when we have two solutions, the graph passes through the x-axis twice. When we have no real solutions, the graph never passes through the x-axis. And when we have one real solution, that parabola like bounces off the x-axis. So it just touches at that, what we call the vertex, that bottom point. Another thing the discriminant is really useful for, actually the way I use it most often, is that if the discriminant is a perfect square, like 1, 4, 9, 16, 25, 36, etc., it means that the polynomial can be factored. So you don't have to go through the whole AC process just to figure out that the polynomial is prime. If you plug your coefficients into the discriminant and you get a perfect square, then you know you can factor and solve by factoring. And if you don't get a perfect square, you have to use another method. So it's a quicker way to figure out if you can factor a polynomial than actually trying to factor it. Keep in mind, the quadratic formula can only be used in quadratic equations. So that's degree 2 polynomial equations. If you have an x to the third in there, you can't solve it using the quadratic formula unless you can like factor out an x.